We will begin this lesson by reviewing how to use the disk method to find volumes of solids of revolution. Then we will find volumes of solids whose cross-sections are not circles. And the final thing we will do is prove some formulas from geometry. For example, no one's ever told you why the volume of a sphere with radius r is 4/3 pi r cubed. Today I will show you why. So consider the region bounded by the curves f of x equals square root of x and g of x equals x to the third. Set up and solve an integral for rotating this region about the following axis. So first of all, we have the x-axis. In the 4 parts of this example, we are going to take this region and rotate it around 4 different axes. You'll see the volume is different each time. So here we have f of x equals root x. Here we have g of x equals x to the third. The intersection points are 0, 0, and 1, 1. And in this example, we are going to rotate this region about the x-axis. So in this particular example, this region will have the cross sections you slice will go this way, and we will have a circle with a hole in it. So the area of our cross section is pi times the outer radius squared minus pi times the inner radius squared. So r out is the distance from the axis of rotation to the outer curve. In this case, that is root x. R in is the distance from the axis of rotation to the inner curve, so that would be this distance. In this case, that is x cubed. So the area of a slice is pi times square root of x squared minus pi times x cubed squared. To find the volume, I need to add up all my slices, so I integrate from 0 to 1, factor out the pi, and inside my integrand is x minus x to the 6th. You can work out all the details on your own. For these problems, I really care about the setup, since that is the hardest part. If you have access to Wolfram Alpha or a calculator, I would suggest first setting the integrals up, checking to see if your answer is correct with a device, and then trying to work out the details. For this particular example, when you work out everything, you end up finding that the volume is 5 pi over 14. In this example, we rotate the same region, but about the y-axis. So once again, we have our root x function, and we have our y equals x cubed function. We will spin this time about the y-axis. So we will slice perpendicular to the y-axis, so that is a slice, it spins. Once again, we will have a hole in the cross section, so the area of a cross section will be pi r out squared minus pi r in squared. Now r out is the distance from my axis of rotation to the outer curve. So the outer curve is y equals x cubed, but this distance is a horizontal. I need to have this equation solved for x. So that is x equals y to the 1/3. So my outer radius is y to the 1/3. My inner radius is the distance from the axis of rotation to the inner curve. That inner curve is y equals root x. Once again, we need to isolate x, and we will have x equals y squared. So in this case, my inner radius is y squared. And so the area is a function of y. The area of a cross section is pi times y to the 1/3 squared minus pi times y squared squared. To find the volume, we must add up the areas of each individual slice, so we integrate from 0 to 1 once again, factor out my pi, Now y to the 1/3 squared is y to the 2/3 minus y squared squared is y to the 4th dy. So that will be pi times the antiderivative of y to the 2/3 is y to the 5/3 times 3/5 minus 1/5 y to the 5th, evaluated from 0 to 1, giving you 2 pi fifths. In this next example, we will rotate the same region about a line that is not the x or y axis. So let's graph our region, same thing. Y equals root x, y equals x cubed, about the line x equals 1. That's the vertical line right here, going through that point of intersection. So there is x equals 1. So this is more like rotation about the y-axis, so we will slice like this. And once again, my cross sections will be circles with holes in them, so I have to find the outer radius and the inner radius. So r out, that is the distance from my axis of rotation to the outer curve. So this total distance between there and there is 1. And we solved this in the last example for x. This is x equals y squared. And this one is x equals y to the 1/3. So for the outer radius, that distance is 1 minus y squared. And for the inner radius, that's the distance from my axis of rotation to that inner curve, that will be 1 minus y to the 1/3. And using that, the area, my area of a cross section is pi times 1 minus y squared, the quantity squared, minus 1 minus y to the 1/3, the quantity squared. To find the volume of pi times the integral from 0 to 1, I'm going to also expand those just to show you how. So 1 minus y squared squared expands into 1 minus 2y squared plus y to the 4th minus 1 minus y to the 1/3 squared expands into 1 minus 2y to the 1/3 plus y to the 2/3. So we'll have pi times the integral from 0 to 1 of y to the 4th minus 2y squared plus 2y to the 1/3 minus y to the 2/3 dy. And sparing you the antidifferentiation details, when you do antidifferentiate and then plug in 1 and plug in 0, you end up with 13 pi 30ths for this particular volume. In the last example, we will consider the same region spun around a horizontal line, specifically the line y equals 2. So y equals root x, x cubed, and y equals 2 is up here. So in this example, my slices will go that way. So r out, the distance from my axis of rotation out to that blue curve. So remember, that blue curve is y equals x cubed. So in this case, r out is 2 minus x cubed. R in is 2 minus root x. You should remember that x cubed is the distance from there to there. So 2 minus it gives you the black length of that black line. So the area of a slice is pi times 2 minus x cubed, the quantity squared, minus 2 minus root x, quantity squared. And to find the volume, I will integrate, take out the pi, integrate from 0 to 1 once again, 2 minus x cubed squared minus 2 minus root x squared dx. Now if we expand, pi times the integral from 0 to 1, 4 minus 4x cubed plus x to the 6th minus 4 minus 4 root x plus x dx. And combine like terms a tad before you get to differentiate. Pi times the integral from 0 to 1, we'll say negative 4x cubed plus x to the 6th plus 4 root x minus x dx. And once you work out all the details, you should get 55 pi over 42. Next, consider the region bounded by the curves y equals x squared and 4x minus x squared. Find the volumes of the solids generated by revolving this region about the following axes. So first, the x-axis. So y equals x squared goes through the points 0, 0, 1, 1, and 2, 4. And of course, has symmetry about the y-axis. So here is y equals x squared. Now 4x minus x squared, the best way to graph that is to find the x-intercepts. Take out the greatest common factor of x, that leaves us as x times 4 minus x. This is equal to 0 at x equals 0 and 4. So you know that this graph crosses the x-axis right there and right there. And let's just plug in the values in the middle to get a picture, an idea of where the curve is. So when you input 1, we get 3. When you input 2, we get 4. Oh, intersection point, look at that. When you input 3, we will get 3 again. So there we have our region. The points of intersection are at x equals 0 and x equals 2. Now, I will take the region between the blue curve and the black curve, and we are going to rotate that region about the x-axis. So my slice will look like this. So the outer radius in this case is equal to 4x minus x squared, and the inner radius is equal to just plain old x squared. But now you should get the idea. The volume will be pi times the integral from 0 to 2 of r out squared, so 4x minus x squared, the quantity squared, minus x squared squared. And once you work that all out, you should get 32 pi over 3. If you're not certain that you can do that, you should stop right now and try to work it out. All right, next. So same region, just about the line y equals 6. So there's the y equals x squared, 4x minus x squared, y equals 6 is somewhere up here. So if this is my general slice, r out, the distance from y equals 6 to the outer curve will be 6 minus x squared. R in, the distance from the axis of rotation to the inner curve, that will be 6 minus, now be careful of this, 4x minus x squared. You have to take away the entire y, which means you need parentheses, and that simplifies to 6 minus 4x plus x squared. So to find the volume, we integrate from, well, have the pi out in front, integrate from 0 to 2. Our slices begin at 0 and end at 2. Pi r out squared, so 6 minus x squared squared minus 6 minus 4x plus x squared squared dx. And if you work out the details, this should give you 64 pi over 3. And I'd like to mention, if you're going to work out the details, one thing. When you square 6 minus 4x plus x squared, it's useful to do this. Squared means multiply the base by itself, like this. And then this just becomes a massive distribution problem. First, you distribute the 6 to everybody, and that gives you 36 minus 24x plus 6x squared. Next, you distribute the negative 4x to everybody. That will give you negative 24x plus 16x squared minus 4x cubed. Last, you distribute the x squared to everybody, and we get plus 6x squared minus 4x cubed plus x to the 4th. It is easy to get lost in all those details. Personally, I like to line up like terms so that I can just add them vertically when I combine them. So feel free to work that out on your own. Thus far, all of our cross sections have been a circle or a circle with a hole, which is, two circles. How can we handle shapes with cross sections which are squares or triangles or rectangles? So what we are going to do is very similar to what we did in the past. Now the volume is the integral from a to b. You add up all the areas of the slices, multiply by their thickness. It just happens to be in all the previous problems, my areas were all of the form pi r squared because my areas were all circles. So if the cross sections are perpendicular to the x-axis, meaning you slice this way, we are going to use x's. And you can think that this is delta x and that delta x parallels this dx. If we instead slice perpendicular to the y-axis, we will then have a delta y, and my areas are functions of y. So a of y dy. And this c and this d will be the lowest y to the highest y. Let's do an example. So find the volume of the solid in the picture below. The base of the solid is the region bounded by f of x equals 1 minus x over 2, and g of x equals negative 1 plus x over 2. The cross sections perpendicular to the x-axis are equilateral triangles. So first let's take a look at this solid. The lower picture is a picture of the base, and the upper picture is a picture of what the solid will look like. When we slice here, we get equilateral triangles that are pretty large, but as we move our slices more toward 2, the size of the triangles gets smaller and smaller. So the first thing we need to figure out is to find the area of our cross section. We need the area of an equilateral triangle. So consider the following. Suppose we have a triangle, an equilateral triangle, where all the sides have length s. So this is s, and that's s. We know that the area of a triangle is 1/2 height times the base. In this triangle, we know the base, we do not know the height, so let's figure that out. So that is my height. Well, because of symmetry and some geometry, this will divide this bottom base in half. So this side right there has length 1/2 s, as does the other side. And we can now use the Pythagorean theorem with this triangle right there, that one, to figure out the height. The Pythagorean theorem tells us that 1/2 s squared plus h squared will equal s squared. Now 1/2 s squared, we get 1/4 s squared plus h squared equals s squared. Subtracting the 1/4 s squared, we end up with h squared equals 3/4 s squared, or h will equal square root 3 over 2s. Thus, the area of my equilateral triangle is 1/2 times root 3 over 2s. That's my height. The base is s, or a equals root 3 over 4s squared. So the area of an equilateral triangle of side with side length s is root 3 over 4s squared. So that is where that comes from. Now let's use that formula to find the volume of this solid. So we know for an equilateral triangle with side length s, the area of that triangle is root 3 over 4s squared. So in this case, what you need to do is find the length of a side for this particular example. Now here, the length of a side is the distance between those two curves. And the way to find that length is to do the top minus the bottom. So the top curve is 1 minus x over 2. The bottom curve is negative 1 plus x over 2, which simplifies down to s equals 2 minus x. Thus, the area of my cross-section, a of x, is equal to root 3 over 4 times 2 minus x squared. And the volume, to find the volume, I need to add up all of my slices. So my slices begin at x equals 0, and they end at x equals 2, so my integral goes from 0 to 2. I'm going to factor the root 3 over 4 out, and I will expand the 2 minus x squared. 4 minus 4x plus x squared dx. And that yields root 3 over 4 times 4x minus 2x squared plus 1/3 x cubed, evaluated from 0 to 2, which gives you root 3 over 4 times 8/3, and that simplifies down to 2 square roots of 3 over 3. So, no circles, no pi. Let's do another one of these. Suppose we have a solid with circular base radius 1. Parallel cross sections perpendicular to the base are squares. Find the volume of the solid. So the first thing you must know is what a circle of radius 1 has for its equation. So that's x squared plus y squared equals 1. The top half of the curve, if we solve for y, if we isolate y, we end up with y equals plus or minus the square root of 1 minus x squared. So the upper half of this curve is expressed by root 1 minus x squared. The lower half, negative root 1 minus x squared. Parallel cross sections perpendicular to the base are squares. So we can actually, in this problem, slice either way. I am just going to slice perpendicular to the x-axis like this. So this is the bottom of my solid, and when I slice it, we get squares. Think about a loaf of bread. That is a circular base, and when you slice it, you get square pieces of toast. The pieces on the end are very small, and you don't get as much bread, so you're unhappy. But the pieces in the middle are the biggest, and they get smaller as you go towards the end. Similar idea. So the area of my cross section, because it's a square, is side squared. What we need to find is an expression for the length of a side. So the reason that the length of a side is not just root 1 minus x squared is because that is just the distance from here to here. So the length of a side will be twice that, 2 root 1 minus x squared. Now to find the volume, I need to add up all of my slices. My slices begin at -1, they end at 1, and I add up all the individual areas, and each individual's area is 2 root 1 minus x squared, quantity squared, dx. Because we have an even function, we can find twice the integral from 0 to 1. And when I square everything, I end up with 4 times the quantity 1 minus x squared. That 4 can factor out of the integrand, giving us 8 times x minus 1/3 x cubed, evaluated from 0 to 1, which gives us 16 thirds. In the next example, we have a similar base, but in this case our cross sections are equilateral triangles, not squares. So a solid has a circular base of radius 3. So -3, +3, +3, -3. And I will slice perpendicular to the x-axis. So there's a general slice. Now the equation for a circle of radius 3 centered at the origin is x squared plus y squared equals 9. Solving it for y, we end up with y equals plus or minus the root 9 minus x squared. Now in this case, the area of a cross section will be root 3 over 4 side squared. So we need an expression for the length of a side. And in this case, the distance from the x-axis up to the curve is root 9 minus x squared. So the whole side is twice that, 2 root 9 minus x squared. So to find the volume, we must add all the slices up. So you will have root 3 over 4. Now, I am just going to right away say twice the integral from 0 to 3 because of the symmetry. And the area of each slice is this root 3 over 4 times the quantity 2 root 9 minus x squared, the whole thing squared. We continue simplifying and we end up with root 3 over 2 times the integral from 0 to 3 of 4 times the quantity 9 minus x squared dx. Multiplying that 4 by root 3 over 2, we get 2 root 3. Now we antidifferentiate and we have 9x minus x cubed over 3, evaluated from 0 to 3, which yields 2 root 3 times 27 minus 9, which is 18, which gives us 36 root 3. In the final component of this lesson, we are going to prove some of the formulas that you know for volumes of 2 geometric solids, the sphere and the pyramid. Somebody told you back in the day that the volume of a sphere with radius r is 4/3 pi r cubed. And maybe you asked why, and the teacher said, I don't know, it's in the book. This is why. So we are going to start. So a circle of radius r has equation x squared plus y squared equals r squared. Solving that for y, we end up with y equals plus or minus the square root of r squared minus x squared, or just the top half will give us root r squared minus x squared. And the thing to notice is if you take this curve from negative r to r, and you rotate that about the x-axis, that will give you a sphere. So we can find the volume of this solid of revolution using the techniques we learned in this particular section. So in this case, my cross-section, I make a slice. Because I'm spinning, my cross-section will once again be a circle. So the area of that cross-section will be pi times whatever my radius is squared. And in this case, my radius is the square root of r squared minus x squared. So my cross-sectional area is equal to pi times the root of r squared minus x squared all squared. Now to find the volume, I need to add the slices up. So I will have an integral from negative r to r, pi times r squared minus x squared dx. That root got canceled. Now take out a pi, and also because of symmetry, I will find twice the integral from 0 to r. So 2 pi integral 0 to r little r squared minus x squared dx. Now the tricky thing here to observe is that little r squared is just a constant, it's a number. So antidifferentiating little r squared is like antidifferentiating 9. The antiderivative of 9 is 9x. The antiderivative of r squared is r squared x. And x squared's antiderivative is 1/3 x cubed, evaluated from 0 to r. And we're almost done. 2 pi times, that will be r cubed, minus 1/3 r cubed. So 2 pi times 3 over 3 r cubed minus 1/3 r cubed. You see that's 2/3 r cubed, so we end up with 2 pi times 2/3 r cubed, which gives you the familiar formula for pi over 3 r cubed. And that is why your geometry teacher did not prove this formula to you, because it is calculus and you didn't know calculus yet. In this example, we will prove that the volume of a pyramid with a square base is 1/2 HB, where H is the height of the pyramid and capital B is the area of the base. Now, let's also just define that the base looks like this, sides little b, so capital B is equal to lowercase b squared. So here is what our pyramid looks like if you look at it straight on. The width of the base at the bottom is lowercase b, and the height is h. Now in this case, we are going to slice this way, and those slices will yield squares. The squares near the base are bigger than the squares near the tip. Now what we need to know is what the area of a general square is, and to do that you need to use a little bit of geometry, similar triangles. So call this B prime, and the height up to that slice is y, which makes the height of this little bit up there h minus y. Now using similar triangles, B prime over B will equal, so B prime corresponds to the base of this little triangle. So the height of that little triangle is h minus y over the height of the whole big triangle, which is h. And that tells us that B prime is equal to h minus y over h times b. And that is useful because once we know what this distance is, we can find the area of that cross-section by squaring this. So the area of a cross-section is B prime squared, or B over h times h minus y, that whole thing squared. So to find the volume of my period, I must add up all of my slices. So I integrate from, now in this case, the slices begin here at the base where y is equal to 0. They end up here at the top where y is equal to h. So we have the integral from 0 to h of b over h times h minus y, the quantity squared, dy. And that gives us b squared over h squared. Those are constants they can factor out of our integral. 0 to h. When I expand h minus y squared, I end up with h squared minus 2hy plus y squared dy. Now anti-differentiating, I get b squared over h squared times h squared y minus hy squared plus 1/3 y cubed from 0 to h. Plugging everything in, I have b squared over h squared times h cubed minus h cubed plus 1/3 h cubed, which gives us 1/3 b squared over h squared times h cubed, and that simplifies down to 1/3 b squared h as needed.